We live in an era where complex mathematics is offloaded to computer solvers. We type an equation, hit enter, and trust the output as absolute truth. But algorithms have blind spots. When faced with transcendental or high-degree algebraic equations, solvers frequently fall back on numerical estimations, or they output imaginary complex branches that do not actually exist in physical reality. A transcendental equation is one that contains non-algebraic functions, like sine or cosine, making it resistant to standard algebraic solving. A 2026 paper by mathematicians Charmley and Steve Konrad exposes exactly why this gap between estimation and physical reality matters. Their work bypasses floating-point approximation entirely. They use classical analytical techniques to prove the exact physical reality behind incredibly stubborn equations. The proof targets 4 specific objectives. First, it isolates the exact real solution sets for 2 mathematical objects, known as the light and dark witnesses. From there, the paper defines a unique derived number called the dorc constant. And finally, it classifies every exact solution of a massive 64th-degree polynomial system. To understand these mathematical objects, we must look past approximations on a computer screen and rely strictly on the unyielding logic of formal proof. This animated diagram displays our first target, the light witness equation, 13 sine squared of x minus 21 sine of x minus 34 equals 0. To solve this, we start with a standard algebraic substitution. By replacing the sine of x terms with the variable u, the transcendental equation collapses into a familiar quadratic format. 13u squared minus 21u minus 34 equals 0. Like any standard quadratic, this can be factored cleanly into 2 distinct linear expressions, u plus 1 and 13u minus 34. Because u represents the sine of an angle, it is bound by the strict limits of trigonometry. The real sine function can only ever oscillate between -1 and +1. Setting the second factor to 0 gives u a value of 34 over 13, which is greater than 1. A symbolic solver might return an output using the arc sine of 34 over 13, but that is a purely formal complex branch. For real numbers, it is physically impossible. That leaves exactly one mathematically valid branch, u equals -1. This means the sine of x is -1, which perfectly isolates our first target, the principal light root, at exactly 3 pi over 2. By applying rigid algebraic boundaries, we filter out the theoretical artifacts generated by machine computation, leaving only the exact real number. This next diagram shows the dark witness equation, simplified as g of x equals 55x plus 42 cosine of x plus 13 sine of x times cosine of x equals 0. Unlike a simple quadratic, this equation combines bounded trigonometric waves with an unbounded linear term. Our task is to prove that it crosses the 0 line exactly 1 time. We achieve this using calculus. Taking the derivative of g of x gives us its rate of change, which factors cleanly into 2 times 1 minus s times 13s plus 34, where s is the sine of x. Again, the value of s is locked between -1 and +1. Because of this boundary, neither of the factored components can ever be negative. This guarantees that the derivative is always positive, a condition known as strict monotonicity. Strict monotonicity means that the area under this derivative curve is constantly adding up, forcing the original function to continually increase without ever dipping down. Next, we apply the intermediate value theorem. The intermediate value theorem is a calculus principle stating that if a continuous function moves from a negative value to a positive value, it must cross 0 somewhere in between. By evaluating the extreme ends of our function, we see it goes from -infinity to +infinity. It has to cross 0. And because the curve is strictly increasing, it can only make that crossing exactly once. A numerical solver can plot points and estimate where that 0 lies, but calculus provides absolute proof that this single, isolated dark root exists. This animated diagram illustrates the dorc. It is defined by taking our principal light root, 3 pi over 2, and pairing it with the unique dark root we just proved, creating the formal ordered pair, d. From this pairing, Charmley and Konrad construct the dorc constant. They take the ratio of the light root over the absolute value of the dark root and raise the entire quantity to the power of 1/8. Using the rigorous bounds established earlier, we can calculate that this constant is approximately 1.3088. The 1/8 exponent is a deliberate human choice. It is an intentional piece of the definition, not an inevitable output forced by the underlying witness equations. Because its parent roots were rigorously proven, the dorc constant is a mathematically exact reality, anchored by proofs and immune to the compounding errors of floating-point arithmetic. This equation represents the double-orc system. It is a massive two-variable structure built on 32nd and 64th powers. Attempting to calculate the roots of a 64th degree polynomial directly through brute force or standard algebra is practically impossible. Instead, the paper uses dimensionality reduction. By defining two new variables, u and v, to represent the 32nd powers of x and y, the massive exponents are factored out. This substitution flattens out the incredibly dense polynomial geometry, collapsing the entire system into a single, highly manageable quadratic equation. To find the exact number of real solutions for this new equation, we calculate its discriminant. The discriminant is the specific portion of the quadratic formula, located under the square root, that determines whether the roots are real or complex. Computing the discriminant for this specific equation yields a strictly positive number in the billions. Because it is positive, mathematical law guarantees exactly two real roots for the variable u. Through strategic substitution, we bypass the terrifying complexity of high-degree geometry, reducing an unapproachable problem into standard, solvable logic. This animated diagram maps our final results. Solving that quadratic gives us two distinct, strictly positive anchor points, labeled u1 and u2, along with their corresponding v coordinates. To work our way back to the original x and y variables, we apply the mathematical rule of lifting. Because 32 is an even number, every positive real number has exactly two real 32nd roots, one positive and one negative. We have two positive anchor points, and each anchor splits into positive and negative roots for both x and y. Two anchors multiplied by 4 sign combinations yields exactly 8 real branches. These 8 specific coordinates are the double-orcs. But if we look beyond real numbers and step into the formal complex plane, the landscape expands aggressively. In complex geometry, each coordinate holds 32 theoretical roots, rather than just a positive and negative pair. This means each anchor point lifts to 32 roots for x, multiplied by 32 roots for y, giving 1,024 complex solutions per anchor. Multiply that by our two anchors, and the system produces exactly 2,048 distinct complex solutions. By enforcing strict boundaries for real numbers, we perfectly isolate the 8 physical double-orcs, cutting them out from a chaotic background of over 2,000 theoretical shadows. This generated image summarizes the 4 mathematical milestones achieved in the proof. They were reached not through brute force computation, but through a sequence of strict algebraic boundaries, calculus, and dimensional substitution. We locked down the exact real solution set for the light witness, discarding impossible complex artifacts to isolate the principal root. We used the intermediate value theorem to prove the strict, non-repeating uniqueness of the dorc root. We bypassed a 64th degree polynomial system to classify exactly 8 real coordinates for the double-orc system. And while the resulting dorc constant has no simplified closed-form expression, its mathematical foundations guarantee it remains a flawlessly defined entity. True mathematical precision requires moving beyond the passive acceptance of whatever numbers a solver spits out. We have to rely on classical analysis to strip away complex illusions and isolate the exact, real truth.